In this video, we're going to be covering some thermodynamics problems where you're going to be learning about two situations with a single and double pane window where we're going to be talking about heat conductivity. So we're going to be looking for our change in heat per time, and then we're also going to find our change in heat after 1 minute. All right, so we have a situation where we have a 3x4 single pane window, and then we have one end of the window that's 25 degrees Celsius and the other side that's 20 degrees Celsius. And it has a thickness of 1.5 centimeters. So first of all, we definitely want to do some converting and then convert this into 0.015 meters so that everything is in our standard unit. So 1.5 divided by 100. We also have our heat conductivity constant, 0.8, for this specific piece of glass over here. Now what we're going to do is we're going to use this formula over here. Delta Q over delta T equals our constant times our area times the temperature, our change in temperature, delta T, and then that all divided by L. All right, so we have all of our constants here. We just have to do one conversion, which we already did right over here, and then basically just plugging in numbers from there. So we have our constant of 0.8 joules per second per meter per degree Celsius. And then we also have our cross-sectional area. It's just 3 times 4 to give us 12 meters squared for that area. And then our delta T is always final minus initial temperature. In this case, there's not much of a final and initial. You just have a region that is hotter, which is obviously the 25 degrees, transferring heat to the region that is colder. So 25 minus 20 is 5 degrees Celsius as our delta T. And then our L value is basically representing that thickness, which we converted to 0.015 meters. So from there, we just have to multiply 3 numbers across for our numerator and then divide by 0.015. Then we get a value of 1,920 joules per second. Okay, so that is our first solution. And then for our second one, if we are looking for just the delta Q within 1 minute, all we would do is one more simple calculation. We know that this equals delta Q over delta T. We're going to convert delta T from 1 minute to 60 seconds. Multiply both sides by 60, which is basically crossing that 60 up and over. And then we have our second solution for our delta Q, which comes out to 115,200 joules of heat energy transferred in a minute. So those are our two solutions right there. Okay, so if you're analyzing one of these problems, if you need to do a bit of converting, such as the 0.015, that is pretty typical for a window pane problem because a lot of these windows aren't going to be a meter thick. From there, it's just a lot of plugging, making sure you're taking care of your variables to get your two different solutions. All right, let's go ahead and check out this double pane window problem, one that's slightly more difficult, and see if we can go ahead and solve this one. Now for our second problem, it's going to be a little bit more complicated because we've got 3 layers here. We have 2 K values. The 2 outer levels, or outer layers, excuse me, are the glass, and then the middle layer is air. So what we're going to do is we are still going to take our Ka delta T over L formula, but we're going to do a little bit of rearranging to count for all the 3 layers. So if we divide everything by K, then we divide the numerator by K, and that would cancel that out, and we did not divide the denominator by k, and it would look like that. So then we're not actually changing the value of it if we're dividing everything by the same value. And then from there, what we can do is to incorporate all three layers. We're going to take the area times the delta t, and then incorporate the L over k for each of the layers involved in the problem. Now, the L value is going to be pretty consistent. We have the outer layer of glass, the inner layer of air, and the next outer layer of glass as well. So all we have to do is some plugging in here. Again, we have a 3x4 window, so it's going to be 12 meters squared. Our delta T is from 10 to 20, 10 degrees Celsius as our heat transfers from one side to the other. And then also on the bottom, we have an L value that we have to convert. So remember, we do 1 centimeter and then 100 centimeters per 1 meter, which turns out to 0.01. All right, so we have our 0.01 as our L value, which is the length that the heat travels across, which is basically just the thickness of the window. And that 0.01 is going to be consistent for each one of our layers because each layer is 1 centimeter thick according to our initial setup. And then we have 3 different K values, but in this case, 2 of them are the same because the outer 2 layers are glass. So this one's going to be 0.8. This one's also going to be 0.8. And then the middle layer for air is 0.024. So what I'm going to do is I would typically just use my calculator to add up all these fractions to get my denominator. I know the top is 12 times 10, which is just 120. And then I would get 271.70 joules per second, also commonly called watts as well, the amount of joules of heat energy transferred per second through all of those layers. Now, for this type of problem, it's not really that much more difficult than the single pane one. You just want to make sure you implement this little trick here to incorporate all the layers, and then from there, it's just punching a lot of little numbers into your calculator to get your final solution. So I hope that was helpful to you and helping you learn about single and double pane window problems and heat conductivity. Thank you for watching and listening.